Sure, go
Well,
ahead.
great. Well, good afternoon, everyone. This is Dr. Liz Pierce, and I've got Dr. Sirhan Dagtas with me. And this is Data Science and Technology, and we are fully remote today. So Dr. Dagtas is here. He has a great deal of expertise and practice with multimedia. So to kind of set the context of where we are, in data science, we started off with statistics, which is I want to say, one of the early branches of data science. And we talked about some of the techniques for working with numeric data like counts and measurements, as well as working with qualitative data that represents, for example, various categories or states an attribute might take on. And then we moved on from more structured data to unstructured data like text. And so we spent some time looking at the type of information that you could glean from text. Well, we're going to be moving on to some other data like images, but the multimedia is an area that I think is very exciting for data science, because this is where all this data comes together. And I can remember years ago, I think it was the Little Rock police wanted to create a fusion center. And the vision of the fusion center was that they could collect all these different types of data, and that they would be able to make sense of it and be able to use it for real-time decision making. And years ago, that fusion center, it was a great idea. I'm not sure if it went anywhere, but the technology is advancing that I really think fusion command centers are going to be possible. And so the idea that in the event of an emergency, if you're FEMA, if you're disaster relief people, wanting to collect all this data. For example, think of all the data that would be coming from sensors in terms of counts, measurements, state data in terms of things like closed versus open, active versus inactive. Think about all the text messages that people might be sending. Think about the signals, location data coming from cell phones. Think about the video that people might be transmitting, or the pictures they might be sending. Imagine if you could take all of that information and use it, for example, to update your maps as to which roads were accessible and to what types of traffic. If you could update your maps showing where people needed to be rescued. Imagine if you could pull in some of the technologies to help process this data and to update this data and put it in front of people so that they could make really good real-time decisions as to where resources and assistance was needed. And so this is really exciting. And so I really felt this was very important to have Dr. Dagtas talk a little bit about multimedia, because I really think in terms of the power of data science, it's not that we're looking at each data type in silos, but when we can start to bring together all these different data, all these different types of data, and be able to integrate them together, that's where I think you really will see the power of data science. So without further ado, Dr. Dagtas, I'm going to turn the lecture over to you to talk to the students about storage and retrieval of media data.
Thank you, Dr. Pierce, for the great introduction to the matter. You have already done part of my job for today, but I'm really pleased to be, co-teaching this class, covering certain areas which are very important, as you have laid out, to the field of data science in general. Our plans was, of course, to kind of meet in person today and get to know each other with students, which we had to change the remote for this week. But hopefully we will get a chance to do that next week to see some of you also in class and continue this. So I just turn my camera on so we can, or you can see me and we can get a chance to at least see each other face to face. But I'm going to keep my camera off to maybe ironically not to make this presentation as multimedia as we might like to, because some people may have slow connections. Sometimes the audio quality suffers. So let me know at any point if you have any questions or if we actually need to talk. But my plan is to start with an introduction to the area today. From the context of data science and a little bit with an, just a little bit of an emphasis on databases, because that's the area I come from. Before the data science term became so popular, many of these research fields and applications, including multimedia field itself, found its roots in the field of databases, as some of you may know as a background in the area. So multimedia as a concept was basically an extension of many database capabilities early database management systems had. And today, data science being a much broader area that involves also some database concepts still, borrows and is based on a lot of the base technologies this field has come to develop over the past 3-4 decades. So we're going to basically take a look at what multimedia, term really refers to in a more popular sense, as well as from a technology perspective, what the implications are from a more data-centric perspective, whether it's data science or in particular, database applications, what the challenges are, of course, what the opportunities are. We have already witnessed this so-called multimedia revolution from even a more practical sense. If you recall, one of the popular social media sites that is known as, interesting, X today, even way before the name was changed to X from Twitter, there was already a basic transformation of the data in Twitter. If you know the early days of the Twitter platform, it was basically meant to be a very short text-based messaging system, similar to what the SMSs were trying to do. SMS, as you know, means short messaging service. The idea was to keep the amount of data as short and small as possible, so you can make it practical, basically, on the early days of low resource days of wireless communication. And Twitter, to most people, became a popular platform because of that simplicity as well. And the same can be said for other things like HTML language being so simple, all text-based, XML exchange platforms. Similarly, many of these successful technologies owe their success to being simple and brief and practical. But then we saw, as resources became more abundant in terms of transmission, communication, and of course storage and computation resources, we saw also this transformation from being monomedia to more multimedia in terms of what you can handle, what you can capture, what you can transmit, and more recently what you can interpret through many AI techniques and also the widespread use of the AI related technologies. So we are still witnessing that, which started as more inclusion of multimedia data in our practices, like including non-text data in the platforms like Twitter. Today, many of the the posts on X, Twitter, or similar social media sites will also include non-text elements, as you may be seeing. So there are platforms like YouTube or Instagram or many others that are solely multimedia based, image, video, audio, etc. But even the traditional text-based platforms, technologies, and applications are turning more and more multimedia. So this, of course, is made possible by improved resources available. It also brings new challenges and opportunities to the field, especially the data science field. So we're going to look at some of those ideas and challenges, and even techniques have been around for quite some time, for 3-4 decades, but they are being put into more widespread use, and they're basically going through more, wider acceptance by the users, as these things are becoming more and more common. So multimedia, as the name suggests, involves more than 2 media types. So it typically involves the extension of the simple alphanumeric text-based data into more human-like media types, like that you can hear, obviously see, and even in some cases they can sense and smell, and in other ways that are more that cater to humans' sense of the real data, the real world. So when you include at least 2 of these types, images and text, images, audio, etc., typically that system, that application, that database, or that networking system, or that AI system in some cases, it can be called a multimedia. So that includes both the visual and, in many cases, audio, and even other dimensions like haptics and motion and sensor data, and etc. You obviously have to deal with more data or more complex data in terms of both quantity and quality, or the description and semantics. So an image can be worth 1,000 words in a literal sense also, and a video can be worth 1,000 images in a quite literal way as well, because videos will consist of several image frames. And of course, this is true also for audio. Any continuous media type will involve a lot of bits and bytes. They will also involve a lot of complexity, much of which has not been completely explored yet, even with the advanced AI techniques today. So the multimedia data presents both many new opportunities and also challenges, and that issue continues to be the case. The human-computer interaction, the humans' interactions with these computer applications or systems, etc., can be improved, or can also be complicated with multimedia data. So if you have the capability of, for example, reading gestures with a camera, or through other means, in fact, even with things like laser sensors and devices like that, so you can interact with a computer system, with a social media site, with your device, etc., in much more sophisticated ways. But you also need methods and ways to understand and interpret both human side to enter data in a completely new way, and also to have to take care of the computer side to improve and take advantage of this new dimension of interaction capability. So and this falls into more, the field of data science, also ways to represent, interact, and navigate through the richness of the data and the resulting information that you can produce from your data. So some people like to refer to this idea of inclusion of new data dimensions in terms of multimedia data as second information revolution. But in either case, this brings a lot of new complexity and opportunity to the field of data science and information technology in general. So the size speed, to some extent, has been addressed with the new technologies like 5G in wireless and advanced networking and much cheaper computing and storage resources. But the challenges in semantics is still an issue. So I mean, many of you are graduate students. Of course, you're also shaping up your thesis work and developing ideas around that. So the dealing with semantics, the rich meaning of information that can be stored and represented in images, video, etc. It remains still a fairly open research area and with a lot of challenges and research opportunities in that place. So in a more formal way, a multimedia database involves multiple types of data, as you can imagine, not just the traditional numbers and text, as many database systems would do, but also the inclusion of objects or images or video records, animations, which can be vector graphics, audio, video, or IoT information, IoT data, haptics, etc. All kinds of data, different dimensions of data may be included in a multimedia database system, and multimedia database management system obviously is a system that can be capable of handling with that data. And different multimedia database systems have handled this challenge in different ways. You may have heard of object-oriented databases, object extensions, or sometimes the hybrid object relational database model, and an entirely new non-SQL or maybe non-traditional database approaches have also been developed to address the database aspects of the multimedia data field. So in addition to different types of multimedia data, many of these systems, whether it's a database or any data-centric application, will have to deal with many, just in terms of number and the size, large amounts of data in terms of multimedia objects. So the storage management with that large amount of data in both the numbers, the quantities, as well as the individual sizes of objects, present its own challenges. So models like hierarchical storage models have been developed and used for this. And obviously, you cannot just handle an ordinary multimedia data just like any other alphanumeric data. So many of the traditional approaches like relational databases and the algebra data and the theoretical foundation developed for that purpose may not, and it typically does not answer the requirements and the challenges of the multimedia data. The areas like persistence, concurrency control, recovery from failures with multimedia data. So all these areas, including the security and copyright management, things like this, provide their own challenges when you include multimedia data in a database or a database application. But probably the most interesting and challenging aspect is the information retrieval or data retrieval. So you can just go to your database if you have a record of employees with salaries. You can just run basic queries on them, you compute the average, join tables and apply certain criteria, get people with certain salary levels and things like that. So whether it's numerical operations or or string-based operations or selection criteria or retrieval techniques, that's a fairly well-studied and mostly taken care of area. But the retrieval of information, just the description, the accurate description of information alone in your multimedia data is still an unsolved problem to most extent. So there are obviously many dimensions this has been tackled, and many application areas, successful application areas like face recognition, for example, for security systems have been developed, voice recognition, speech to text, text to speech. So some basic problems have been solved or mostly solved, but still in terms of representing and retrieving information, we're just basically scratching the surface. So if you have a collection of images, for example, compared to a collection of data records with maybe some simple information like names of people or salaries or social security numbers, date of birth, things like that, the richness of the information in traditional data is much simpler to represent in numeric or text dimensions, or even in the semantics of the words. But if you have a collection of images, even in your personal collections, many of us have these, at least on our phones, many images, just describing these images beyond things, the metadata that may represent them, like the date of capture, maybe who may be in those pictures, they may be recognizing a few faces. So beyond these few features that you can think of, all that information is not fully represented by many of the multimedia information systems. So retrieval techniques like representation of the semantics, exact or partial matches, the other retrieval methods like probabilistic or content-based or metadata-based ranking and coming up with the best matches are still a big challenge. And these are, important challenges already, even in alphanumeric data. If you do a web-based search, if you go to Google, you can always argue for or against the ranking of results. For example, sometimes these are shaped by other concerns like advertisements, paid results, etc. We know that, but beyond that, from a more technical perspective, even alphanumeric data still has very rich semantics that may or may not be captured by many of these representation or retrieval models. And this is even more so for multimedia data, as you can imagine. So if you move from images to video, you add the time dimension, the audio on top of many images you already have. So it becomes even more complex, as you can imagine. So the data formats, whether for images or moving images or videos or audio or even other types of IoT data, also brings a lot of variety, and of course makes it also challenging to build any capable multimedia capable information system, whether it's a database management or any other information retrieval based idea. So some of these formats will be familiar, like the popular JPEG and MPEG standards in this area, which provide great compression capabilities and in some cases some semantic descriptions. Some are industry standards, some are more proprietary to different platforms. Many will provide some additional security features. So these image formats and the handling of images in different formats can even be a big challenge. A lot of times when you may see this on the websites, when you try to upload certain documents, some formats will be acceptable, some will not, so you'll have to worry about conversion. So even the representation, just the non-semantic representation of media content can be a big challenge in itself. And of course, the data size and varying quality metrics when it comes to compression of this data, and varying size metrics and requirements, especially for time-based data and video, can be another big challenge. So when you're dealing with a lot of data, whether you're doing anything with the semantics in it, the content-based representation, or simply dealing with things like conversions, data conversions, or storage, or even playing back, the processing time and the resources it takes can be another challenge for many applications. And the representation of the time dimension or the temporal dimension for video, audio, or even synchronized multimedia presentations is also an important part that you don't find in many traditional data or the information systems dealing with only alphanumeric data. So different type. We mentioned a few of the data types. So in this part of the class this week and next week, we are going to get a bit deeper into some of these data types, look into some of these specific techniques to handle different types of data. So you did cover already some of the text analytics methods as part of this class. Since we're talking about multimedia, many of these multimedia the databases, the multimedia information systems, multimedia techniques will involve a lot of times some kind of text analysis, or they will include the text as an dimension, as another dimension of data. But in many multimedia-based systems, one other dimension, one other media type will also be part of this. So text presents its own challenges. There can be, of course, a lot of semantics issues with respect to understanding and interacting based on text data. But in a multimedia system, text is typically used to support and complement other forms of data. You may have, for example, image captions, the correlation or relationship between captions or headings of images or videos or video posts can be an important part of interpreting that data. So the text can be, in addition to being a media type by itself, can also be a complementary data, or sometimes referred to as metadata, to non-textual or other forms of data. This can be structured or formatted using different techniques. XML is a good example as a markup language. And of course, we humans are used to representing text in terms of visual symbols with fonts in different alphabets and in different languages. So audio is the next in line in terms of maybe data size, typical data size. There are some uncompressed and compressed audio formats that we kind of came to know. MP3 was a pretty popular format in the early days of digital audio. The CD, so the CDs or CD formats would be converted to MP3 formats with good compression. So you can fit basically more audio recordings in a smaller amount of space. And other proprietary formats like WAV format for a Windows platform, or others for Apple platforms or other platforms may or may not prefer, have been developed also with the widespread of streaming platforms and streaming technologies. Some formats have been developed for streaming purposes, for real-time transmission of audio and also the video format. So when you digitize audio, as we will discuss in greater detail later, so you sample your continuous data, and that can result in a lot of data uncompressed. But good compression techniques like MP3s and even better ones nowadays can compress that data in 10 to 15 times to 1 ratio. In other words, your 12 megabyte uncompressed audio can be represented as a 1 megabyte file in compressed with minimal difference in quality. And we will see some techniques, not great detail, but some techniques that can be used to achieve this for both audio compression and video compression purposes. Just like vector graphics, if you're familiar with the term for images, the formats like MIDI format or structured audio, part of the MPEG-4 standard, can also represent music in more synthetic form, but with much higher efficiency in terms of space. MPEG-4, if you're not familiar with this, is a video compression standard used more commonly for streaming purposes and also for efficient storage of video clips. So you may another important media type obviously is digital images. These images are basically raster images are the images that are captured from the real world. So these are represented, as you may know, as a two-dimensional data structure, a number of pixels that may represent the color value at every pixel or at every tiny point as either in black and white color, sometimes grayscale, meaning still black and white, but some gray values, different number of gray values may also be part of the image, or full color images, in which case each pixel or each pixel element, each point would be represented as a combination of 3 color values. RGB is a good example, red, green, and blue. So when you represent a real world scene with a two-dimensional sampling or collection of color points, you run into this quality issue. Obviously, the more pixels you use for this, the better or the closer you get to the real world representation. So this has to do with the resolution. Of course, we see this in descriptions of screens, even mobile phones, big TVs that we buy are also measured in terms of the pixels they can display. And cameras, of course, are measured in terms of how many pixels they can capture. So this resolution becomes a very important dimension of that image representation or the quality of that image representation, since you're essentially sampling, taking only a subset of the real world description of an image. That resolution becomes an important quality metric. And typically these images, when captured, as you may know well from the images that you take with your phones or other cameras, will be in the form, in the range of megabytes, 1, 2, or 10 or 20 megabytes, etc. Typically in compressed. So to obviously make that process more efficient, more manageable, many image formats, including JPEG and later versions of JPEG, like JPEG 2000, JPEG 2, or TIFF, PNG, etc., use compression techniques, lossless or lossy compression techniques. So lossless compression, as you can imagine, it means you can recover the data exactly in its original format. Many of our file compression techniques we use to represent files like zip, etc. Obviously, you don't want to lose part of your file when you recover it. So those are lossless techniques. But media compression can also be done through lossy techniques, which means whether you're compressing your audio, image, or video files, you will not be able to fully recover your file or media type in its original form. But the differences may be unnoticeable or acceptable depending on your subjective evaluation. So lossy compression can actually take advantage of certain dimensions of data that we cannot see or hear or sense anyway. And without even much noticeable difference, compression ratios of about 1 to 10 can be achieved, which can make a huge difference, especially for video or large image compression. This can basically mean the difference between life and death, right, for a lot of digital media types. For example, the DVD format for videos, late 90s and early 2000s, was only made possible because of the lossy compression techniques, MPEG techniques back then. Because a movie, a full feature 2-hour long movie, could now be fit into a 4 gigabyte DVD at the time, thanks to these lossy compression techniques. Without proper compression, that movie uncompressed would take probably in the order of 20, 30 gigabytes, which would not be possible to fit on an optical media device at the time, so we wouldn't see any DVDs at the time. So compression can actually make a huge difference in representing data, and then, of course, you can making use or taking advantage of what that data may represent. So whether audio, image, or videos, compression, or proper storage and representation of data, even in its raw format, can be important and can be a challenge in itself. So the graphics or visual data can also be represented in terms of vector graphics. In this case, you represent the visual elements through models, through objects, geometric objects, color areas or patterns, etc. So this can be a lot more efficient. Obviously, you don't try to capture or sample in a real world video, so you don't have just some pixels here, rather some objects that may represent the shapes, areas, etc. So in terms of space management, the data size, these can be very efficient, and they will also be scalable. So if you ever dealt with a PDF document, you may have noticed that if you zoom in real close to the PDF document, you can actually scale this up and down. But if the document is an image-based document that has a finite resolution, sometimes PDFs also will have just images on them. So if you zoom in real close, you will notice the difference in on a vector graphics-based representation, object-based representation. Since it's all symbolic, object-based, things can be scaled up and down when you zoom in and out. This is true for other applications like CAD, the GIS, etc., computer-aided design. Even for simple document representation like PDF, vector graphics can be efficient, but obviously this only works for model-based representation or vector graphics. So you can't take an image that you capture with your phone and turn this into a vector graphics representation. And in documents can be integrated, involving different dimensions like video or text. And there, sometimes you have some kind of a synchronization model. So you may, for example, have a bunch of presentation slides like we're using today. There may be some audio accompanying that, and then and when the two dimensions are integrated, combined into a single document, then you'll have to deal with their co-management or representation or
or also the synchronization, time-based synchronization, and issues like this, which is also covered with some standards like SMILE, as this next slide mentions. So the digital video is one of the most complex in terms of the data size and dimension, and also data richness among multimedia data types. Obviously, when you digitize a continuous media type like video, there are several dimensions. You first of all, each instance, time instance, or each frame will have 2 dimensions, just like any other image. And typically you capture several of these every second to provide continuity, and this may take minutes, hours, or even longer. And in many cases, you may have real-time synchronized audio that goes with it, and that audio as a separate dimension will have to be captured, stored, and compressed and integrated with your sequence of frames for a full description of your video. So the compression here and representation in its just raw format is done in several dimensions, both spatial dimensions in terms of space X and Y coordinates, and of course the temporal dimension. There's a third dimension. And the same is true for the semantics of the data too, from a more data science perspective. Representing data in its raw format is one thing, and it's challenging enough in terms of the volume of the data. And then you have equally and perhaps more so, the complexity of the data or the richness of the semantics involved. So just to give an example, in an image, you can have a more simpler description, like color-based description. What is the dominant color or colors in your image? What are the important objects? What could be the representation in terms of keywords or other representations? But then in the video, you also have the additional time dimension. So all these descriptions can be done separately for each frame. And then the third dimension, the temporal dimension, the dynamic nature of the change in content and the correlation between successive frames and frames that are farther apart from each other can complicate things even further. So this is true for representation of the raw data in itself, and it's even more so for the complex relationships and the semantics that may be involved in the video data. So we will see some aspects of this, starting with the low level or maybe physical or raw features aspects like compression, transmission, and decompression. So you may remember this from early days of television, the early standards, video standards of TV standards of analog TVs or analog video also had some frame rates set, like how many frames per second you need to capture. Most people, at least, I mean, this can vary from person to person, can be tricked in perceiving successive frames like continuous capture of the real world when you go over 24 frames per second. And many analog standards actually use this idea of 24 or 30 frames per second, and digital media formats today also try to capture at least 30 frames per second, of course, for better temporal precision, better quality. TVs and video capturing techniques try to go over that, and they can go at 60 frames per second or higher. And when you shop for a TV nowadays, you may see this description, 100 hertz, 200 hertz TVs. This also is a quality metric that can show the refresh rate of the TV's display mechanism that can make a difference in high motion video, like if you're into sports, you may, for example, want to get a higher refresh rate, which means the image on your TV will be refreshed more frequently if that's a higher number, so that you may get a better, higher quality representation of the actual motion that may be happening in that video recording or video transmission. So that high amount of data will have to be dealt with good representation and compression techniques. MPEG compression techniques for the past couple of decades or 3 decades have been the dominant technology in that area, but other formats for streaming purposes have also been developed, some of which are listed here. So MPEG 2 was an early standard used in DVDs and early digital broadcasts. MPEG 4 was developed after that, and some successive technologies. So we will discuss some of those technology details in these multimedia data types. Many data science applications, including database management systems, use the concept of large objects. Sometimes these are called blobs or slobs, etc., blobs. But a large object basically can, as the name suggests, can store and handle large amounts of data, which will be necessary for if you're dealing with a lot of multimedia data in your information system. And the large objects in many database applications or data science implementations have been used to extend the capabilities of the traditional data applications or the databases to non-traditional data, including multimedia data objects. A binary large object is basically a collection of binary data that is stored, and these can be used to store images, audio, video, etc. And database management systems will have basically their own ways to handle with or deal with these blobs or binary large object models. Many of the traditional data requirements or database requirements, like integration, and data and program independence, and concurrency control, so that you can basically deal with multiple concurrent transactions at the same time. Obviously, with any system that involves access to data, you'll have to handle multiple transactions at the same time. So these traditional requirements will also need to be handled with their own challenges in a multimedia involving database management system, including persistence. So data can basically persist the application or the operations that operate on them. Privacy and copyright management is even more important with multimedia data. Images, videos, of course, audio recordings can have access, privacy, and copyright issues specific to them. Query support requirement is probably one of the most challenging aspects of multimedia-based databases or database management systems, because when the querying languages or query systems have been developed along with the data models for traditional data representation models, relational being obviously the most common and most successful one, but they're all centered around the alphanumeric data and its requirements. So when you have the multimedia data stored in your system, accessed and represented, the querying mechanisms or to the ways to represent data that you're looking for may equally be interesting and challenging. If you have been to the Google site, which I'm sure you have many times, the traditional ways to enter a query or a database search term in that case, or a web search term, is by entering keywords. As you know, you can enter single keywords or a combination of them, sometimes phrases. Nowadays, these search engines are turning more and more like AI interfaces, so you can even pose questions in the form of full meaningful sentences, but they're all typically in words, right, in alphanumeric data. There's an equally interesting feature on Google site, which we will check a little later in the class. You can already do that, but you can actually provide an image as a query, meaning it's one of the most simplest ways to represent what you're looking for, to describe what you're looking for. This is called query by example. So you present an example, an image, and the web is searched not for the words that you're looking for, but for the image based on a similarity metric. Obviously, if there's an exact image that's exactly the image that you're presenting, that image would have the highest rank. But then any images deemed to be similar to the example image that you're presenting as your query can also be included based on the rankings of similarity using the similarity metric that may be used. Of course, that similarity you can imagine can be in terms of full qualifications, like the color, the dominant color, the amount of color, maybe some objects. Could be in terms of metadata, the keywords that may be associated with that image, etc. So the similarity metric can be defined and implemented in many different ways, and that's one of the interesting areas and challenges in multimedia data, whether it's for images, audio, or video. How do you even describe? How do you develop some kind of a description in what dimensions? And then how do you apply certain similarity metrics or other metrics for any other purpose for a simple task like querying or retrieving data from your collections. So that image-based, example image-based querying already implemented on the Google site is a good example, but querying or providing queries or query languages or query processing, retrieving data is actually a hugely challenging and complex task that has been the subject of many research activities in the past few decades. So we talked about the query, the storage and presentation and delivery aspects. So these are the different dimensions and areas a multimedia-based database management system or any data-based system or information system will have to handle and take care of. Are there any questions or comments so far? I'm still going through a kind of a long introduction, so I didn't pause much for any comments or questions, but if anybody has anything to add or ask or say at any point, please do let me know. So we're going to complete this introduction probably, if not today, sometime on Thursday. So we're going to start seeing some more, implementation and applications of these. And we are also going to discuss a short exercise that you guys will be able to do with some of these ideas in place. So let me know if you would like to add or ask anything, even during this introduction.
And Dr. Daktis, I will keep an eye on the chat. So far, no questions.
Sure. Thank you. So we have, I think, he made enough emphasis on the complexity and sophistication the multimedia data types and dimensions can bring to the data applications, databases, or the field of data science in general. So the point that I'd like to emphasize within this context is basically just a few examples that you can see and check some of these concepts in action. So we are already familiar with some of these concepts of keyword-based browsing and searching, obviously, and keyword-based searching methods have been around. But some searching and retrieval mechanisms involving the music, like searching by humming and things like this, basically providing some audio example to search for a melody or search for images based on the paintings and certain similarity metrics that can be developed around that. So there are some examples to that effect also. And you can imagine many application areas, some of which are already in place. Obviously, with real-time streaming, there's many, learning and educational opportunities. Video-on-demand services have been widely in use with streaming services, which used to be a video-on-demand VOD was basically a theoretical model in terms of networking and other issues up till 10 years ago or so. Nowadays, it's in commonplace. So in terms of storage, accessibility, representation, I think the industry has overcome many of the problems already. Now, with the advancements in AI, it seems to be the time for actually making use of all that richness in the information, whether it's in the audio or video, or even other dimensions like sensory or IoT data. So in so-called intelligent or expert systems, with AI or machine learning techniques, will now be able to have access to vast amounts of data that they can process, learn from, and utilize. In addition to these other application areas, with like audio on demand, video on demand, streaming services, e-commerce, obviously, remote education, digital libraries, and even other areas like medical information systems. So we will see many of these application areas in the near future being enriched by not just making the media data available, like streaming services is already here, so you can access vast amounts of video recordings, real-time, live, or on an on-demand basis. But as a next step in the next decade or two, we will also see the technologies enabling, not in terms of the infrastructure and availability of data, but also in interpretation and utilization of the information, not just the data, but also the information, and then the knowledge and perhaps the understanding of the rich semantics, especially found in multimedia data. So many of these technologies have already supported and are supporting the use and inclusion of multimedia data. Obviously, computational resources and display, capturing in terms of scanners, cameras, microphones or audio systems that can capture audio in multiple dimensions, networking technologies, wireless and fiber, and local area, mobile, 5G, 6G, 7G generation, new generations of wireless networks, the high capacity, solid state, and other technologies that can support large storage spaces at much lower costs. The software that can do both image and video processing at the low level processing of data, like things like compression, conversion, capturing, digitization, etc., as well as the high level, which will be perhaps the next phase in capturing the meaning and semantics of the multimedia data. And object recognition, face recognition, OCR, object character recognition, to convert images to text, or speech to text, or face recognition and ID recognition systems have evolved tremendously in the past 10, 15 years, so they have become a reality. You can go through immigration lines nowadays just by having your face recognized without even presenting your passport. So that the industry has come a long way in some of those areas already. So to represent and retrieve multimedia data differently from traditional data, what are the key considerations? So you just need to kind of broaden your horizon a little bit. Retrieving traditional data is done in simpler dimensions like string comparisons, alphanumeric ordering, or numeric operations, etc. But data or information that you can represent, or that is already represented in multimedia data, is a lot more complex than that. So querying cannot be as simple as the traditional querying mechanisms. A lot of times this will require some kind of an interaction, since you're trying to capture the rich semantics, and even capturing the real intent of the person, or even an artificial person, right? An AI mechanism that may be presenting a query may be challenging. So you may have to go through several iterations and do this as a more interactive process with some relevance feedback in some cases, refining the query. In many cases, the processing, this querying, and the representation will have to be done in a hybrid manner, meaning semi-automated and semi-manual process. What we mean is, if you're looking, for example, in a vast image collection, certain images that may match the description of what you have in mind. So just basically describing, providing an accurate description of what you're looking for may be a challenge. So if you have an example image and show it to 5 different people, even if they're intelligent, not artificial but real people, 5 different people may come up with 5 different descriptions of what they see of the same image. So that can be a very challenging process, even when you have human intelligence involved, and automating that process, extracting features that may fully represent the descriptions or the requirements or the demands of an intelligent system, and making that process efficient by using proper indexing mechanisms can be quite a challenge, and it is. So many of these systems, some examples of which we may see during this class, involve some kind of a relevance feedback. So if you present a query for a certain type of image you're looking for, and if you're given 10 potential results, right, 10 potential answers, you may be asked to provide some kind of a feedback, for example, as part of your interactive process, and say something like mark the 7 of the 10 that you are being presented as being relevant to what you're looking for. So the querying representation mechanism running in the background can learn from your feedback and fine-tune or refine its mechanisms, both to represent and retrieve data based on your feedback, and next time around you can be given more accurate results. Accurate in quotation marks in terms of what you're looking for. So that will be even among different human subjects that may be, of course, a subjective judgment. So that brings an additional challenge to many of these automated mechanisms. But still, many of these considerations have been addressed and studied quite extensively in the past 20, 30 years. Many successful systems have been developed and are being developed, but still we are not capturing the full extent of the richness of data that is backed, or the semantics that is represented by this data, even for just the single dimensions of image collections, let alone videos and even more complicated combinations of different media types. So obviously the data size becomes an issue here, so the efficiency becomes even more important than the regular database or the data science approaches. So you may need to consider clustering of media data, so you can deal with data in terms of clusters. So being aware of the certain clusters, for example, you can fine-tune your data representation, querying, and retrieval mechanisms based on the clusters your media belongs to, and organize the storage of the larger objects. And the queries can be optimized to best capture and be matched with the dimensions that your data model captures. And also on other dimensions like duplication of data, parallel processing, and scalability in terms of the operations that you perform can be applied to larger sets of data. So both functional and efficiency considerations will be important when you are building a multimedia capable data model and ways to represent and process multimedia data for the purposes of storage, retrieval, especially if you're dealing with the content-based nature of data. So in the world of multimedia systems, multimedia data, content-based has a special meaning. So you're dealing with the content itself rather than the metadata descriptions or keyword descriptions of the images. So you may tag your images on your phone or in a collection with a few keywords, and you can be searching your images with those keywords. That's metadata-based searching. Or you can just describe a certain type of image, for example, images with a certain person in them, even without any tagging or metadata, etc. You can do a content-based retrieval. A lot of phone applications nowadays, image collections already do that. You may see things like collections of your pictures with a certain person. They can be pulled off without any manual tagging. So using simple face recognition techniques, these image applications can bring the images of certain persons present, and those pictures can be retrieved from a larger data set, and you can see those done pretty accurately nowadays. So this is an example for a content-based representation and retrieval of data. So you can, from a larger set of data, images, you can, for example, capture images of not only certain persons, but maybe involving certain objects, any nature images, for example, from a large collection of photographs that you may have captured, any images that may involve sunset or any other content-based description based on the image or content itself. And for videos, that will need to involve not just imagery or visual features, but also the time dimension, or in some cases, it may involve also the audio. So you may be looking for music videos, for example, that may have some music in the background, or videos involving certain actions in sports videos, or maybe in security cases, you may be looking for certain video clips or areas of your video that may involve certain events happening. Things like that will refer to the content of the video rather than the keywords or metadata that may represent the data only in a limited fashion. Obviously, when you're relying on your metadata, you're reducing the dimensionality or the complexity of your data. So you're only relying on certain aspects or part of the semantics that is involved. So this can present many advantages, or it can also bring in many challenges to the field. And we will be visiting some of those in the context of either individual media types or combination of those. We will be visiting some of these challenges and see some techniques on how these challenges can possibly be addressed to make the multimedia data part of any content-based retrieval mechanism or representation mechanism. So you can apply also many of the either database techniques to include the new media types in database management systems, or in a broader sense, to apply many of the data science-based techniques, including AI and machine learning, so you can actually not just include and utilize the existing data, but also perhaps learn from them, and even to be able to create content-based data, or the content itself based on the large amounts of data that may be present. So we can, this content-based retrieval can be done in different dimensions depending on the media type, image, video, etc. We have discussed some of these. So I'm going to leave you guys with kind of a sample multimedia scenario, just so you can continue thinking about this between now and next class, and basically just develop some understanding and appreciation of what what this multimedia area can bring to the data science field in general. So you can imagine a police investigation that may involve obviously multiple types of data. Audio data can of course be audio recordings from phone conversations. Surveillance cameras or security cameras can provide the video dimension. The cameras that people use or investigators use can provide the image. Written documents can be, of course, be another source of information. Structured relational data. This is the data that you can go to a traditional relational database or data source and obtain, whether in the form of tables or other structures like XML data, etc. And any GIS or geographic information system data. So think about ways that you can represent and query these different sources of information in different media formats. And we're going to pick up from this point and complete this introduction and get into the specific data types and look into some of the techniques that can make inclusion of these new media types possible in information system or in an application scenario like this police investigation story. Any questions, comments, please let me know.
And I was going to say, Dr. Dagtus, if you have any slides that you'd like me to post in the Blackboard course shell for the students, just let me know. I'd be glad to post them. And I was really quite fascinated watching this because, so often in data science, we're so eager to start analyzing and applying the data. But to build these applications, I hope the students can see how much planning, how much trying to figure out where you're going to obtain the data, how are you going to store and share and retrieve and manage the life cycle of that data. Those are so critical because without that foundation, the analysis is just not possible. So it's really good to get this context of what has to be in place for us to really make data science and things like machine learning and AI possible.
Absolutely, and we can only, even as humans, understand and capture only a small part of what the multimedia data presents to us, and our information systems capture even less of that. And I think there's just so much more work that can be done in this area. So it's an area that grows as you actually spend more time and effort on it. And even in this class, we will only be able to obviously cover only parts of these important aspects, but it's going to be an interesting part of the class, hopefully. Thank you.
Well, I think
but in terms of slides, I'm going to just email you these slides that I'm presenting today. I looked for ways to put them on the Blackboard, but you may be able to do it easier. So I'll just email them over to you.
Oh, I'd be glad to, because we're using Blackboard Ultra, and it has all the same capabilities as regular Blackboard, but they've managed to find different places where you need to find those capabilities. So,
sure.
Excellent. Well, everyone, we will see you on Thursday. Keep an eye on your email to see where we will be on Thursday. So if the campus is open and the roads are safe, we can hold it in class. But again, if the roads are still icy on your street on Thursday, remote will be fine. And Dr. Dagtus, that goes the same for you as well. Depending on where you are in the city, some people may have clear streets on Thursday, and for some folks, it'll still be too treacherous.
Sure, we all will keep a close eye on that, and I wish everybody, safe day and night, and just, be careful with that.
All righty. Well, again, thank you so much, and thanks for everyone who turned out this afternoon. And once the recording has finished processing, I will get that posted for anyone who'd like to refer back to this for reference. So take care and stay safe, and we'll resume again on Thursday.